Okay, so we're just going to keep building on the methods we've been developing for solving recurrence relations. But before we do that, I just wanted to do a quick recap of the type of stuff that we already know how to do. So we started in the very, very beginning with first order homogeneous recurrence relations. These were super easy, right? You've got something of the form an is equal to, let's say, c times an minus 1 for, let's say, n at least 1, right? Then what you end up with, your solution is basically an is c to the n a0, right? Okay, and then if you wanted to find some specific solution, you just plug in a value for c0, or sorry, a0. Okay, these were really easy. Then it became a little bit more challenging when we got to first order non-homogeneous recurrence relations. So this is something where you have, for example, an is c times an minus 1 plus f of n for n at least 1. Now for this, we developed this kind of telescoping sum approach where we take, we take this, we write it as an minus c an minus 1 is equal to f of n. We then have something like this for the previous term, dot 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 a1 minus c a0 is equal to f of 1. You can multiply every line by c or some power of c. So the first one is c to the 1, the last one's going to be c to the n minus 1. And like, if you think about it, how this telescoping thing works, it's always kind of the same thing, right? You end up with, on the left side, an minus c to the n a0 is equal to some kind of a sum. So let's say the sum k equals 1 to n of like c to the n minus k f of k, right? So this basically gives you a formula for an in terms of some multiple of a0, some exponential multiple of a0, plus some sum k equals 1 to n involving f of k. So c to the n minus k f of k. And like, I mean, at this point, you usually want to turn the sum into like some actual expression. And to do that, you use what you use the formula for f of k. So if it's if f of k is like 6 to the k or something, then you plug that in and you work it out. Basically, I mean, to figure out what the sum equals, usually it just ends up being based on these standard things. So if I have 1 over 1 minus x to the m, it's the sum. Let's say maybe I'll write it with k because this sum has a k. So k equals 0 to infinity. K plus m minus 1, choose m minus 1, x to the m, to the k, right? So basically these things always boil down to kind of trying to get things in this form so that you can get a formula. By the way, so this, I mean, what I've written here is actually a general solution to every first order linear non-homogeneous recurrence relation. But probably you shouldn't just memorize this formula because that might not be good enough, right? You should actually know how to derive this formula rather than just memorizing it. So I might ask you, for example, you'll see on the assignment, you're asked to use this telescoping method to find a formula for an. So you should know how to do this in practice. Okay, then we had second order linear homogeneous relations, and this was kind of even easier because than the first order. I don't know why I keep on saying first order non-homogeneous cases, because this just boiled down to so for this one, this type, we do just have a sort of thing we can memorize. So you take the characteristic equation, you take the roots of the equation, which could be complex numbers or real numbers, and if R1 is not equal to R2, then the general solution is A R1 to the n plus B R2 to the n. And that includes the case where R1 and R2 are complex. And if R1 equals R2, then AN is A times, well, R1 to the N plus B times N times R1 to the N, where like I wrote R1 both times, but you could write R1 and R2, but they're equal, so it doesn't really make a difference. Okay, so this is how to find the general solution, and as usual, when you find the general solution, you can find a particular solution by plugging in some initial conditions. Okay, so next, what we're going to do is kind of build on this to the next most complicated thing. So we had first order homogeneous, we then had first order non-homogeneous, we then had second order homogeneous. Now we're going to look at second order non-homogeneous. So imagine AN is of the form C times AN minus 1 plus D times AN minus 2 plus f of n for some function f of n, okay? Where C and D are constants. So what we're going to see here is a bit more of the magic of generating functions. So basically, we're going to use generating functions. Okay, so what I can do is, basically the idea will be to take your equation. Well, first let's perhaps say we want to define a generating function fn to be the sum of n equals 0 to infinity an x to the n. Now, if you take your recursive kind of equation and you multiply both sides by x to the n, okay, on the left side you've basically got a term of your sequence, the sequence that defines the generating function. Or I guess what I mean is like you've got you've got an x to the n, right? And usually these, the recurrence relation kind of equation is valid for, let's say, n at least 2. So the equation that I wrote down to begin with is true for n at least 2. So if you could take this thing and you could sum this over all n equals 2 to infinity. So on the left side, I have an x to the n, and on the right side, you could write this as 3 different sums, right? So you have c times the sum of n equals 2 to infinity, an minus 1 x to the n, and then plus d, the sum n equals 2 to infinity, an minus 2 x to the n, plus the sum of n equals 2 to infinity, f of n, x to the n. Okay, where, of course, this little f is different than the big F, right? And the key thing here is, I guess, that on the left-hand side, what you've got is exactly f of x minus a1 times x to the 1 minus a0 x to the 0. Because basically, this sum looks exactly the same as the definition of f of x, capital F of x, except that this sum starts at 0, whereas this one starts at 2. Okay? Otherwise, they're exactly the same. So this should be f of x minus the term n equals 1 and the term n equals 0. And then this sum here is also pretty much the same as f of x, except there's, again, there's a term that's missing, and then there's also the fact that this starts at, that the n here in the exponent is different than the n minus 1 here, but that can be fixed by just pulling out an x. So I can write this as c times x times the sum n equals 2 to infinity, a to the n minus 1, x to the n minus 1. And similarly here I can write d x squared sum from n equals 2 to infinity, a to the a sub n minus 2, x to the n minus 2. And then here I've got, again, the same sum I had before, so n equals 2 to infinity, f of n, x to the n. Okay. And now the key is that basically this is pretty much f of x again. So this is just going to be f of x minus the 0 term, a0 x to the 0. And then this sum is just equal to f of x. And then basically you can just take this equation and solve for f of x. Okay, and that will give you your generating function, and so on. Okay, this is, right now what I'm doing is writing this in a very general setting, which might be a bit tricky to follow. So it's probably going to be easier if I just give you a specific example, and we'll see how this works. But the principle here that I'm kind of demonstrating here is kind of the key thing. All of these questions essentially will sort of boil down to the same thing. Okay. By the way, also, if you look at, we've also got this other term here, right, that I haven't talked about, this term involving the non-homogeneous part of the equation. I can see that it's not that easy to see. You've got the UVic thing on top of it. Anyways, but basically, again, just like in the when we're doing the telescoping, we hopefully this is going to be something which we can figure out the solution for because of some of the things we know about generating functions from earlier. Okay, let's look at a specific example. So here I've got an is equal to 2 times an minus 1 minus an minus 2 plus 2 to the n plus 2. So let's define the generating function. And by the way, this equation is valid, let's say, for n at least 2. Okay, and I want to find the general solution. So yeah, so let's define f of x to be equal to the sum n equals 0 to infinity of an x to the n. So now if we can take our original equation here, which is valid for all n at least 2, and we write it down and multiply both sides by x to the n. So multiply both sides of the recurrence, or maybe I should say the recursive definition of an or something, by x to the n. So that's kind of usually going to be our first step. So we take the recursion, multiply this by x to the n, and multiply this by x to the n. And then next, what we want to do is sum this equation over all values of n such that the recursive definition is valid. So what I mean by this is here we defined an in this way for all n at least 2. So what I want to do is take this equation, which is true whenever n is at least 2, and I want to sum it over all the values of n at least 2. So the left side ends up being the sum n equals 2 to infinity x to the n times an, or maybe I'll write it the other way around, an times x to the n. And let me give myself a bit more space here because I'm going to have a lot of sums. So this is now equal to the sum from n equals 2 to infinity. So there's a 2 here, so I'll put the 2 in front. So 2 times an minus 1 x to the n minus the sum from 2 to infinity an minus 2 x to the n plus the sum of n equals 2 to infinity 2 to the n x to the n plus the sum n equals 2 to infinity, I'll put a 2 in front of that, x to the n. Okay, we've got a lot of sums here, but the good thing is that we know what some of them are. At least, so for 3 of these sums, we can express it in terms of f of x, where f of x is our generating function defined here. So these 3 terms are going to be expressed in terms of f of x, and then this the last 2 terms here, those are things we're going to be able to work out just because we understand geometric sums, meaning, yeah, 1 over 1 minus x is the sum n equals 0 to infinity of x to the n. I mean, basically that's what's going on in those 2 sums. Okay, so the first one, the first yellow one here, we can write that this is f of x, except the first 2 terms are missing. So minus a0 x to the 0 minus a1 x to the 1. The second sum, so the first sum on the right hand side, we can pull out an x, and we can start the sum at 1 instead of 2. Then we get an x to the n. Okay, I've kind of gone quickly through that, but the point is, so if I pull out an x here, what I would have here is an minus 1, and this would be an n minus 1 here, right? But if I start that sum at 2, where I've got an n minus 1 everywhere, you could think of that as starting the sum at 1 and plugging in n instead of n minus 1. So that's all I'm doing here. The next sum, we can pull out an x squared, and we can write that this is the sum for the same reasons as before, n equals 0 to infinity, an x to the n. And the next sum, there's lots of choices for how to deal with this. I feel like the easiest thing to do is to pull out a 2 squared and an x squared and write that as the sum n equals 0 to infinity 2 to the n x to the n with this pulled out. The last sum, again, let's pull out an x squared, and then we have the sum n equals 0 to infinity x to the n. Okay, now let's do some algebra and stuff like that. I guess we should also, at this point, we should recognize that this thing is f of x minus a0 x to the 0, and this thing here is just f of x. So let's plug that in. Well, let's keep the left-hand side the same. So we've got this is equal to 2x f of x minus a0 x to the 0, then minus x squared f of x plus, so what's this? So the sum of 2 to the n x to the n is the same as 1 over 1 minus 2x. So that's what we get for this. That's just one of these standard generating functions. And then this is the most standard generating function. So 2x squared. Oh, I noticed I'm sitting on top of the some of our equations here. My bad. But this was just copied from the previous line anyway. So our last expression is 2x squared over 1 minus x. Okay, it looks like this is getting complicated, but actually we're in pretty good shape here. So I want to get our generating function f of x, and basically the point is that I can take this expression and solve for f of x. So that's what we're going to do. So this is the last expression from the previous slide. Now let's bring all the f of x's to the same side. So I've got f of x, and from here I get a 2x f of x, and I subtract it to the other side. So I get minus 2x f of x plus x squared f of x. And I've got that this is equal to, and the hardest part of this is not forgetting one of these little terms. But this comes from this moved to the other side. We mustn't forget about the other term here. So that's minus 2x to the 1 a0. And then we've got this same old stuff here. So 2 squared x squared. Okay. Let's put this stuff together. So we'll have a 1 minus x here, 1 minus 2x, 1 minus x, plus 2x squared, 1 minus 2x. So I'm just kind of combining this stuff. Maybe I'm not sure if that was a good idea or not, but, well, we'll see. Maybe I'll end up regretting that. We can always go back. Okay, so now on the left side, I've got my f of x's, and I can factor it out. And then I can divide the whole right side by whatever's left over, which will be a 1 minus 2x plus x squared, right? So, okay. I've got a0 x to the 0 plus a1 x to the 1 minus 2x to the 1 a0. Divide that by 1 minus 2x plus x squared. Hopefully it's clear where I got this, right? This came from my factoring over here. Then I've still got my other stuff here, which all becomes, so maybe I'll just use the copy paste function to bring this over here. Okay. Okay. So I've got this, and then I've also got to divide by the same thing. So 1 minus 2x plus x squared, which, by the way, does this factor? I think it's x minus 1 squared, right? Or 1 minus x squared. Let's go with that, because so this is going to be then a0 x to the 0, a1 x to the 1 minus 2x to the 1 a0 over 1 minus x squared plus, this is getting kind of ugly, but let's multiply this out or something. I don't know. So 4x squared minus 4x cubed plus 2x squared minus 4x cubed over 1 minus 2x. And then what we're going to end up with here is 1 minus x cubed. And you know what? Now I am kind of regretting putting all this stuff together, right? Because actually, maybe this is a good kind of an example of what not to do. Because, I took this stuff up here and I put it together, which, I went from here to here, which felt like a good idea at the time. But why would I do that, right? Because it's not a very good idea, because here's the thing. Whenever we have like some kinds of fractions where you have like the bottom is factored in some way, like let's say we have 1 over 1 minus 2x, 1 minus x or something. I mean, usually at the end of these proofs or at the end of these solutions, what we want to do is use partial fractions to split these up. But if we're trying to split these things up, what was the point of putting them together? So let's kind of, in some sense, I'm going to in order to make my life easier, I'm going to sort of assume that I never put those things together in the first place. So, and what that's going to mean is, so when I went from this step to this step, I'm going to kind of think of it as if I had never done that. And so instead of dividing, this expression by 1 minus 2x plus x squared, which is 1 minus x in brackets all squared, I'm going to imagine that I just divided each of these terms by the same thing, by that thing. So this is maybe instructive. Don't necessarily just blindly do algebra to combine things, because it might actually make the problem harder. So if I had never combined anything, then at this point what I would have is, so from this expression up here, I've got 4x squared over 1 minus 2x and a 1 minus x all squared. Okay, this is from dividing by my 1 minus 2x plus x squared, which is 1 minus x in brackets all squared. And then we've got 2x squared over 1 minus x cubed. And to me, this looks a little bit better than what I've got here. Okay, maybe it's not that much better, but I think it's a little better. Because, so each of these three terms I've got left here, they're things I can deal with except for the middle one. So the middle one is going to need some partial fractions, but the other two are pretty good. So let's just work on this middle term, and then we're going to try to figure out what this is with partial fractions, and then substitute it back in. Okay, so partial fractions tells me I want to write this as a over 1 minus 2x plus b over 1 minus x plus c over 1 minus x squared. So if you multiply everything out, what you get is 4x squared equals a times 1 minus x squared plus b times 1 minus 2x, 1 minus x, plus c times 1 minus 2x. This right-hand side, you can play around with it and get the constant term, the x term, and the x squared term. So you have the constant term is a plus b plus c. You're going to have an x times, so that the coefficient of a, which has, involved with the x, is going to be a -2. So you have -2a. This looks like -3, right? Minus 3b. Minus 2c. If it's mysterious how I got this, you can, do some expanding here in another way. I mean, basically, I kind of assume you guys know how to do this, right? But if any of this is not clear, then I kind of believe that if you were to expand this and multiply things out, you would get the same thing I have, but you just might do some more steps. Okay, so what this tells us is that -2c is equal to 4, right? A plus b plus c is 0, and -2a minus 3b minus 2c is also 0. Oh, wait a second. What have I done here? This is completely wrong. Let's go back a few steps. I don't know why I wrote this down for the quadratic term. The quadratic term doesn't have any c's in it. So it should just be a plus 2b. No idea how I came up with negative 2c. So sorry about that. A plus 2b should equal 4. Okay, so what I'm going to do is take 2 copies of the second equation and add it to the third equation. When I do that, I get 0 a's, negative 1b, 0 c's, and then it equals 0. So therefore b is 0. So now my first equation just becomes a equals 4. And now my second equation just gives me that c is equal to negative 4. So what I end up with is 4 over 1 minus 2x plus 0 plus, well, not plus really, minus 4 over 1 minus x squared. Okay, so I've double checked this, and these are the right values. So, right, so this is my partial fractions decomposition. So, where were we? So we're pretty much there now. I know this is a very long road, lots of steps here, but hopefully I think each step by itself is not too challenging, I hope. But the problem is there's a lot of steps, so it's easy to kind of miss something somewhere. So this is the expression I had before, and now what I'm going to do is I've done the partial fractions on the middle thing, so I can rewrite it as 4 over 1 minus 2x minus 4 over 1 minus x all squared, and then plus this. So I believe this is what I had, right? 4 over 1 minus 2x, 4 over 1 minus x squared. Okay, now what is my general solution? Or my general solution to the recurrence relation? Well, I can just figure it out from this. Again, with a little bit of pain, but okay, let's group things up here a little bit. So I'm going to deal with this stuff which is over 1 minus x squared first. Not really for any good reason, but so I'm taking this stuff and I'm combining it with this thing, right? So what I can write is a0 minus 4 plus a1 minus 2a0 times x over 1 minus x squared. Okay, maybe let me just rewrite some stuff here. So each of these things are things that we can do, we can deal with. So I'm going to write this as a0 minus 4 sum n equals 0 to infinity of n plus 1 x to the n. And then I've got an a1 minus 2a0 times x times the same thing, n equals 0 to infinity n plus 1 x to the n. Now I've got a 4, so I'm dealing with this term now, 4 times the sum n equals 0 to infinity 2 to the n x to the n. Now 2x squared for the last term, sum n equals 0 to infinity n plus 2, choose 2, x to the n. These are just from some formulas we've used a million times now, which I've just memorized. Okay, now we need to we've got all these x's in front of stuff like this one and this one. We need to pull these in and kind of shift all the indices and stuff to make it all match up. So I've got a0 minus 4, n equals 0 to infinity, n plus 1 x to the n, plus a1 minus 2a0. And this is now going to be the sum n equals 0 to infinity of x to the n plus 1, x times n plus 1, which is the same as the sum from n equals 1 to infinity, n times x to the n. Okay, so you've got to be pretty quick with these substitutions at some point. So hopefully you're getting used to these things by now. This one I'm not going to change. I've now got this one, which I should change. So 2 sum from n equals. So you can think of it as 0 to infinity of this thing with an n to the x plus, or x to the n plus 2. But you can also just think of that as summing from 2 to infinity, n choose 2, x to the n. So now I've got everything in terms of x to the n. The only slightly annoying thing is that these sums start at different places, right? This one starts at 1, that one starts at 2, and the other one start at 0. But actually, technically, if you think about it, each of these sums, I could actually start this at 0 because it'll just give me an extra term, which is 0 times x to the 0, which is just 0, right? Because anything times 0 is 0. If I started this sum at 0, that also gives me a couple of 0 terms, which is perfectly fine. So I can actually just write my final answer now. So this is, okay, maybe it's not quite the final answer, but it's pretty close. Sum from n equals 0 to infinity, a0 minus 4 times n plus 1. So I'm going to put a big bracket around everything, plus a1 minus 2a0 times n plus 4 times 2 to the n plus 2 times n choose 2 x to the n. So at the end of the day, our final solution for an, the general solution, is an equals whatever is in here, right? Because an is the coefficient of x to the n in the generating function f of x, right? You may have forgotten by now, but this is this whole thing is equal to f of x, right? And that's the generating function for an. So the general solution for this recurrence relation is that an is equal to this thing. Okay, so that's pretty long, but hopefully all the steps were sort of clear when we did them. Okay, so if you wanted a particular solution with some initial conditions, of course, maybe I give you a value for a0 and a1. You just plug them in, and that'll give you your or your particular solution. Okay, so maybe to try to just So maybe to just try to solidify this a bit and remind you of the steps. So the idea was you start by writing your recurrence formula. So let's say an is equal to, okay, so maybe for a different example, like 7 an minus 1 plus 3 an minus 2 plus, I don't know, n choose 2. Right? So what you do is you now multiply this on both sides by x to the n, which ends up giving you something like this. And then you sum over all the possible values of n for which this is valid. So usually it's going to be like n from 2 to infinity. But let's say that, let's say that, for example, this recursion was only valid for n at least 3. Okay, then what I would do here is I would sum this over all n at least 3. So I'd sum this from n equals 3 to infinity x to the n an, and I'd say that's equal to the sum of n equals 3 to infinity 7 an minus 1 times x to the n plus the sum of 3 an minus 2 x to the n plus the sum n equals 3 to infinity n choose 2 x to the n. Here, where I got the 3 from in the sum is the fact that this equation is valid for n at least 3. So I can plug this in I can write down this equation for every n at least 3, multiply it both sides by x to the n, and sum it over all the values of n at least 3. Okay? And then the key thing to recognize is that if f of x is my generating function, so let's say it's, n equals 0 to infinity, or maybe in this case, if we're starting our sequence at 1, we have 1 to infinity x to the n an, right? Then you notice that this is pretty much the same as f of x, right? So it's just f of x minus the first two terms. This thing is kind of close to f of x. You just pull out an x and subtract a term or something. And then this is also pretty close to f of x. Okay, and then you want to solve for f of x. And then basically after that point, it's just do some algebra to get the coefficient of x to the n. And that algebra, when I say algebra, I mean partial fractions, canceling. Like if you have something on the top and bottom of some fraction, cancel it out, manipulate things, move things around, and get the coefficient of x to the n. Okay, so I recognize I've only done one example here, but the method is exactly the same every time. So take your recursive definition, multiply both sides by x to the n, sum it up, and recognize the different pieces of this, which are basically the same as f of x, maybe with some terms missing, solve for f of x, and then do all of this partial fraction stuff and whatnot to get the coefficient of x to the n. And then the coefficient of x to the n is the formula for an. Okay, so one more thing I want to do is kind of go back to this thing about homogeneous second order linear recurrence relations. Remember those questions where we're using the characteristic equation to get the general solution? I want to justify that this is actually the correct thing to do. And so basically I want to show you how you can derive this kind of thing about homogeneous second order linear recurrence relations using generating functions. So suppose that I didn't teach you how to use the characteristic equation and someone just gave you a generating function of the form an plus c times an minus 1 plus equals, I should say. So an equals c times an minus 1 plus d times an minus 2. And you were asked to find the general solution, but if somebody, now assume that you weren't told about the characteristic equation. So let's find the general solution using generating function. Okay, and then we'll see that actually it turns out to be the same thing as what we would have gotten by using the characteristic equation. Okay, so I'm going to multiply both sides by x to the n as usual, and then we're going to sum this from n equals 2 to infinity. So this is just by now getting pretty standard, I hope. So I'm going to pull out an extra x here to make the subscript match the power of x, and then I'm going to pull out an x squared here again to make the subscript match the power of x. Okay, and let's define our generating function in the typical way. So f of x is just equal to the sum an x to the n equals 0 to infinity. So here we've got f of x minus a1 x to the 1 minus a0 x to the 0. We've got that this is equal to cx. Now, again, I'm kind of skipping steps here maybe. Well, let's go back and not skip steps in case this is not clear to anyone. So if I start this sum at 2 and go to infinity, it's the same as starting at 1 and going to infinity, but then changing the index to be an x to the n. And then you can do something similar in the second sum, but you can start at 0, right? Because if I plug in n equals 2 here, I get a0 x to the 0. So that's the same as plugging in n equals 0, but having an n instead of an n minus 2. Okay, and then we see that this is equal to cx f of x minus a0 x to the 0, but we can ignore that. So then we have dx squared f of x. Now let's put all the f of x's on the same side. So maybe I'll go to the next slide. So we have f of x, looking back, we're going to have a minus cx f of x and a minus dx squared f of x. So minus cx f of x minus dx squared f of x. And we've got that that's equal to, so we're going to move this stuff here to the other side, and we're still going to have an a0 times cx, negative a0 cx. So on this side I get a0 plus a1x minus cx a0. Okay, I think that's right, but you can double check. Okay, so therefore f of x is equal to a0 plus a1 minus c a0 times x all over 1 minus cx minus d x squared. Okay, now what we need to do is try to remember what we're trying to prove. What I want to do is try to find the general solution of the recurrence relation. I've gotten to this point. Normally what I would do here is factor the bottom and use partial fractions to split it up. Now, of course, it's kind of, I've got some sort of general quadratic on the bottom, so I can factor it, but we need to think about what the factors are. So let's go back to our characteristic equation, which was something that looks very similar to what's on the bottom of this fraction, except it's not quite the same. So the characteristic equation was x squared minus cx minus d is 0. Now let's suppose that the roots of this, suppose if I factored the characteristic equation, I get the roots r1 and r2, which might be complex, they might be the same. We need to do this in generality, so they might be equal to each other, or they might be complex numbers, or they might be two distinct real numbers. Okay, now here's the thing. If I take my characteristic equation, if you think about it, if the roots of this polynomial are r1 and r2, and if I look at this polynomial 1 minus cx minus dx squared, the roots are the reciprocals of r1 and r2. So 1 over r1 and 1 over r2. Why is that? Well, if you think about it, if I take this equation, or this, not equation, but whatever it is, expression, and I plug in a 1 over r1, and then I multiply the whole thing by r1 squared, what I get is r1 squared minus c times r1 minus d, which should be 0 because r1 is a root of this equation. But if this is 0, then the original thing was 0 because r1 is not 0. So I suppose there is somewhat of an assumption here that d is not 0, but that makes sense because if d was 0, then actually what I was dealing with here was not a second order recurrence relation. I was only dealing with a first order recurrence relation. So that's kind of different. So we're assuming that this is a genuine second order recurrence relation. So r1 and r2 are not 0. So yeah. So I can factor this, and I can write the bottom of this fraction as x minus 1 over r1 times x minus 1 over r2. Or maybe I want to write this the other way around, so which I can do, of course. So this is the same as writing 1 over r1 minus x and 1 over r2 minus x. Okay, we can now do partial fractions. And this is going to end up being of the form a over 1 over r1 minus x plus b 1 over r1 r2 minus x, as long as a and b or r1 and r2 are not the same. So this has a different form depending on the roots r1 and r2. So it's either going to look like this, or it's going to look like, so this is if r1 is not equal to r2, and if they're equal, you'll get a partial fraction decomposition like this, minus x squared. Now basically the idea is if I take, so suppose I take this first type of expression, multiply the top and bottom by r1, you get something like a r1 over 1 minus r1x plus b r2 over 1 minus r2x. Okay, and maybe, I mean, a and b are just arbitrary constants, so I could just, maybe I'll just call this c and d. So let's say c is equal to a times r1 and d is equal to b times r2. You get something like this, which is equal to, basically this tells you that an is equal to c times r1 to the n plus d r2 to the n, for some constants c and d. So this is exactly giving us what we expected from looking at the roots of the characteristic equation. And similarly, in this case, you get something like a over 1 minus r1x, or maybe I don't call it a, but I call it c or something. It doesn't really matter. I've got what these arbitrary constants are called, plus, let's say, d over 1 minus r1x squared, okay, which is going to give me that an has the form r1 to the n times some constant c plus, well, this doesn't quite look the same yet, but it's going to be like n plus 1 r1 to the n. But I mean, you can kind of absorb this plus 1 just defining other constants like, let's say, e and f. So this is e r1 to the n plus f n r1 to the n for some other e and f, where I guess that, I don't know. I mean, basically the point here is that when I expand this, I get d times n r1 to the n plus d r1 to the n. So basically, I can then put this into here. Okay, so basically what I'm trying to say here is that this whole thing about the characteristic equation, you can prove that using generating functions. Okay, so so this is the last of the 3 videos that I was going to record. I'll also record one more video just because I didn't have any office hours this week, and I think some people might want to see some more examples of these things, so I'll do a few more examples which are coming from the test 3 practice questions. Okay, so so this is the end of the official stuff I wanted to tell you this week, but if you do check out that other video, then I'll see you in that video.